speaker is Dong-Yong.
Hello, I'm Dong-Yong from Yonsei University, presenting real-time optimal planning for redirected working using deep learning. In this work, we proposed a novel predictive redirection controller steered to optimal target using a reinforcement learning called deep learning. Redirected working is a real-world automation technique used in virtual reality. It makes the user possible to explore the virtual environments, which is usually much larger than the available physical environment. By adding imperceptible rotations to the virtual environment, the redirected working guides users not to collide with the limit of physical space as much as possible. And it also provides the highest sense of presence and immersion. The redirected working is implemented by various redirection techniques, and most redirected working algorithms use continuous software redirection techniques. The redirected working algorithms can be classified into generalized algorithms and predictive algorithms depending on the characteristic of the algorithm. So the generalized algorithms are reactive in nature and guide users toward a certain physical space or patterns regardless of a user's intended virtual travel. The knowledge of the virtual environment or prescripting of user movements is required, making these controllers more flexible but also less optimized. Predictive algorithms analyze the physical and virtual environments to determine whether a user can go, cannot go, or is likely to go, then uses that information to guide redirection. Typically, they are forced and MPCred. And we focused more on predictive algorithms. And the predictive algorithm still has several limitations. They require high computation time. And because they use the passes that the users can go to, the uncertainty of user behavior also make them difficult to operate. Also, they do not work without analysis of virtual and physical space. These problems are intricately intertwined. For example, high computation time is often caused by uncertainty of user behavior. So we try to address these limitations. We use deep neural networks to reduce the computation time and use the reinforcement learning techniques to solve the uncertainty of user behaviors and space dependency. Then we proposed the novel predictive redirection controller steered to optimal target. The steered to optimal target lawfully redirects the user through the following process. First, inputs of the steer to optimal target are the user's locomotion data. They include the user's location and viewing direction. Then the Q network receives these inputs and derives the optimal steering target based on the current user's path. The redirector finally redirects users toward the selected optimal steering target. Prior to performing this process, we formulated this problem to Markov decision process. Redirected working can be expressed as a tuple with states, actions, and transition and reward function. First states, user's partial date can be used as a state. These states are transferred to the new states through redirection techniques recursively. And a real function quantifies the selected redirection techniques. The goal is to make the user perform a high reward action than lower ones. Then we made the Q network learn these Markov decision process. During the running process, Q network receives user's partial information and derives the reward for each action. The highest reward action is selected, and the real function reversed of the action. The modified reward is newly run in the Q network, and the same process is repeated again at the state t+1 created by this. And let's talk about more details. The states of tier 2 optimal targets are the user's location and view direction. They consist of 64 consecutive spatial information measured in 0.02 seconds intervals. So they are locomotion data during total of 1.28 seconds. As actions, tier 2 optimal target has 26 different actions. It has 1 for no redirection and 25 different steering target candidates. We have chosen the 25 candidates of steering targets as the intersection points in the 6x6 grid. So one of the most important part, the real function, is designed as follows. If user is in the tracking space, the real function is expressed as the sum of reward W and reward R and 100. Otherwise, it derives 0. Reward W is the negative of the distance between the user and the center. This reward term indicates the safety of the user from collisions. And the closer the user is to the center, the higher the value. Reward R indicates whether the applied action is a redirecting action or not. If the action is a redirecting action, it drives -1. This real term reduces unnecessary redirections. The structure of Q network is as follows. We use the RSTIM, which is useful for processing continuous data as the input layer. And through the 4 fully connected layers, the Q network derives the accumulative real for the actions. You can find more details about the network implementation in the paper. Before the experiment, we have set 2 conditions. The first one is the condition for the size of the tracking area. The size of the tracking area affects the performance of the redirected working algorithm. So we set the condition of 4x4 sized room scale space and 10x10 sized larger scale space. The second one is the presence or absence of a predefined virtual path. This is to test that the tier 2 optimal target works well in environments without a predefined path. So in simulation test, we use the human locomotion model by Fink et al. And we performed 128 runs under each conditions. The figure on the left is the trace of a simulated user in an environment with a predefined path. The right side is without a predefined path. As a result of simulation tests, the tier 2 optimal target showed good performance regardless of whether there is a predefined path or not, whether the tracking area is small or not. Except for larger scales with predefined path, the tier 2 optimal target significantly reduced the number of resets. In larger scales with predefined paths, there is no significant difference between MPCred and tier 2 optimal target. As a terms of rate of redirection, the tier 2 optimal target significantly increase the rate of redirection in comparison to the others. So in the user test, we experiment only in room scale space with or without predefined path. When with predefined paths, the participants are instructed to work along the 3 given paths. When without predefined paths, the participants are instructed to proceed to 10 targets in random order. The 22 subjects participate in these experiments. 20 are males and 2 are females. As a result of user test, steer to optimal target significantly reduced the number of resets in comparison to the others and increased the rate of redirection. As a term of computation time, steer to center is most efficient in computation. For MPCred, the computation time is significantly greater than for the other 2 methods. As a conclusion, the steer to optimal target significantly reduced the number of resets compared to steer to center and MPCred, and increased the rate of redirection. And the steer to optimal target shows an average computation time of 0.763 milliseconds, and it can be used sufficiently for real-time planning. Finally, the steer to optimal target are available even when there is no predefined passes. And it is the end of my presentation. Thank you for your attention.
That's a very cool project. I have a question like Q-learning means it's a model-free learning. So it omits the environment details. So is there any reason why the authors are interested in model-free learning than a model-based learning?
Sorry?
I mean, is there any reason why the authors are interested in model-free learning than model-based learning? Basically, the Q-learning is a model-free learning, right?
It is model-free learning.
I'm sorry?
Model-free.
Yeah, so is there any reason why, I mean, why the authors are particularly interested in model-free than the model-based one? That's my question.
I think the model reference this redirected working problem well doesn't exist. So I think the free model free based learning is more efficient.
Okay, thank you.
You mentioned in the conclusion there's an increased rate of redirection.
Yes.
Is that a good thing or a negative result? I'm just thinking the rate of redirection increase, maybe that affects the detection threshold, like the person like feels that something is being manipulated or something.
The steer to optimal target redirects the users more. Steer to optimal target increase the rate of redirection, but they are under the threshold. So it doesn't matter how much increase did. So as much as possible to increase the rate of redirection to reduce the number of resets, it is okay, I think.
We have one more question. If the next speaker could just come up and set up while Hi. So have you thought about the user experience while redirecting? You're talking about redirecting more, right? So maybe there is a threshold there. If you redirect too much, the user will feel more sickness or anything.
We also tested the SSQ questionnaire. There is no significant difference, but the participants reported that when the steering target changes dramatically, they feel it is abnormal. So we plan to develop about that.